linear correlation. Linear, it's a line. It's a correlation that behaves like a straight line. Remember, a line that slopes this way, this way, this way, that way, that is called a positive slope, or in our case, a positive correlation. A line that slopes this way, that is, as you go to the right, it goes down. You go to the right, it goes down. Lines that slope this way or have negative slopes, or in our case, a negative correlation. If you have a set of points like such, they tend to be close or somewhere close to that line. It has a positive slope. We call this a positive correlation. If the points are very, very close to the line, we call it a very positive correlation. And we have the same thing for negative correlations. If the points are like that, they seem to cluster around that line. We call this a negative correlation. There is a correlation, a linear correlation. If the points are really close to this negative slope line, like these points are, we say it's very, or actually, very positive, very negative, correlation. On the other hand, the points might be all over the place, something like this. We say this has no correlation. And in every case, we are talking about linear. So very positive linear correlation. A very negative linear correlation. No linear correlation. In fact, in this last one, no correlation. So negative linear correlation. Okay. So now, it would be real good if we can quantify this very strong correlation, no correlation, little correlation. Well, fortunately, we can. There is yet another formula that measures the value of the linear correlation. The name for this value is the letter R. And R is equal to N, the number of data points, times the summation of xy. That is, you add up all the x times y's, and then you take away the sum of the x's. That is, you add up all the x's, and then you multiply it by what you get when you add up all the y values. And this gets divided by the product of two square roots. The first one is n times the summation of x squared minus the summation of x, and then we square that result. Need a little more space. Minus the summation of x, whatever that is, square it. Then times that second square root that I mentioned. You do the same thing for y's. That is, instead of x's, we put y's. It's n times the summation of x squared minus this, like I said, y's, minus the summation of y, all squared. It turns out that if R is close to 1, that means you have a very strong or positive correlation, linear correlation. On the other hand, R is close to not 1, but negative 1, you have a very strong negative correlation. If R is equal to 1, you have a perfect positive correlation. Let's write it out. If R is equal to 1, if R is in fact identically 1, then let's actually say those words. You have a perfect correlation. On the other hand, you have a perfect positive linear correlation. If R is exactly negative 1, then you have a perfect negative linear correlation. And if R is 0, then there is no correlation. Turns out that R is always in between negative 1 and 1. This is the symbol for R is in between. You might actually have equals as well. R is in between this value and that value. Now, you might be saying, well, what is a correlation? Correlation exists between two variables when one of them is related to the other in some way. Or in other words, how many hours you study. And this doesn't always work, but usually the more you study, the higher grade you get. The less you study, the lower the grade you'll receive. In fact, I can't see how it doesn't always help. Maybe you don't study very efficiently, so you study a lot, but it only helps a little bit. But nonetheless, it helps. If you study, your grades will go up. That's a positive correlation. If this is study and this is grade, the more you study, the higher your grade is. Again, if you study very efficiently, your grade may go up more rapidly. If you study not so efficiently, it'll go up the more you study, but not as severe. Okay, now, if you have your grade versus the amount of hours you watch TV. If you watch very little TV, say 1 hour a week, you'll have more study time and you'll probably get a higher score. If you watch TV 100 hours a week, you don't have much time to study. This is a negative correlation. Sometimes it's not linear, but we're only going to talk about linear. Maybe when you study a little bit, it doesn't help much, but as you study more and more and more, it really takes off. Okay, that would be a nonlinear correlation. But we're just talking about linear correlation in this section and the next one. So you have a linear correlation if one variable is affected by the other. You study more, your grades go up. You go out more, your grades go down. Okay. So now let's try to find some kind of an R value. Now, when it comes to hypothesis testing, HO will always be there is no linear correlation. There is no linear correlation. What are you talking about? Doesn't happen. That's the null hypothesis. The alternative, H1, is there is a linear correlation. And it's not HI, but H1. You know that. There is a linear correlation. And the test statistic is that little r that we just spoke about. If r in absolute value is bigger than the critical value, we reject HO. Reject HO. Reject that there is no linear correlation. So that means there is one. And we conclude that there is. There is a linear correlation. If, on the other hand, r is not bigger than the critical value, that does not mean it's less than the critical value. It can equal it. If r is not bigger than the critical value, that is, it's less than or equal to the critical value, well then, we failed. See, here we reject HO, now we fail to reject HO. And we conclude, and our conclusion is, we conclude that there is not sufficient evidence to conclude that there is a correlation, a linear correlation. There is not sufficient evidence to conclude there is a linear correlation. There might be. We just haven't gotten enough evidence. Somebody might be guilty of some crime, but we didn't get enough evidence. All right. So this is how you do the test statistics, or you do hypothesis testing. Let's look at a numerical example. An actual example. Okay, the instructions here say to find R, to determine whether, with no E at the end, whether there is a correlation between the two variables using a 5% significant level. Whether there is a linear correlation between their two variables at, or using, let's say using a 5% significant level. Okay. And here's the data. You have some information about the two variables. When x is 1, y is 3. When x is 0, y is 1. When x is 5, 2, and 3, y is 15, 6, and 8. Now, we need to find r from the data, which is n times the summation of xy minus the summation of x times the summation of y all over the square root of n times the summation of x squared minus the summation of x all squared times n times the summation of y squared minus the summation of y all squared. Now we need to decide what columns we need. That is, what information do we need to find R? Well, let's do it piece by piece. First, you need n. N is the number of points. A point is xy. 1 point, 2 points, a third point, a fourth point, a fifth point. Okay, n is 5. So we have 5. The next thing I see, we need to add up x times y. But I don't have x times y. So let's make up these two columns for right now. The column that has x's, and then the corresponding y values. 3, 1, 15, 16, or just 6, excuse me, I'll change that, and then 8. Okay. So like I said, now we need x, y, and then once we get x times y, we add them up. X, y. 1 times 3, 0 times 1, 5 times 15. I'm just multiplying x and y. 2 times 6, 3 times 8, 24. Then I add these up. These two are 15, plus 0 is 15, plus 75 is 90, plus this is 113. Actually, excuse me, 114. So that here is the summation of x times y. Okay, times 114. Then I see minus. It says they add up the x's. Well, I can add up the x's. 5, 10, 10, 11. The summation of the x's is 11. Okay. Times the summation of y. Okay, so now I add up y. 14, 15, 30, 33. The summation of y, 33. Divided by a square root and n. But n is 5. We already talked about that. Now, I have to add up x squares. I don't have that column. So let's make up a new column. Call it x squared. Square the x's. 1 squared is 1. 0 squared is 0. 5 squared is 25. 2 squared is 4. 3 squared is 9. The summation of x squares is, I love tens. 9 and 1 is 10. Plus 0 is still 10. Plus 25 is 35. Plus 4 is 39. Okay? The summation of x squared is 39. Then it says minus. Then it says add up x's. But then square all of that. Well, I already added up the x's. It's 11. So now I have to square the 11. Times the square root of n. Well, n is 5. The summation of y squares. Well, I don't have a heading that says y squares yet. When I look at all my headings, I don't have y squares. So let's make one up. So I square 3. Then I square 1. Where am I getting these numbers that I'm squaring? From y. What do you square to get y squared? Y. 15 squared, 225. 6 squared, 36. And 8 squared is 64. I love those two because that's 100. That's 100. And that's 10 plus 225 is 235. When I add on the 100, I get 335. So the summation of y is 335. Okay, so it's n times the summation of y squared, minus the summation of y all squared. Well, the summation of y we concluded was 33, and that gets squared. Basically, you crank this out on your calculator. 5 times 114 is 5 times 100 is 500, plus 50 is 550, plus 20 is 570, minus 33 times 11, I guess, is 363. 363 divided by the square root of, that's 195. 195 minus 11 squared is 121, times the square root of 1500 plus 150 is 1650, plus 25 is 1675. And 33 squared is, let's work that one out. 33 times 33 is 99, and another 99. It's 9, 18, 1089. 1089. And if you do this mathematics, you get 0.994. You get 0.994. 0.994. And that's our critical value. Okay. The next thing you do is, well, let's make our little bell curve. The next thing you need to do is compare it to the value you get from the table, from the R table. Okay. Actually, I'm sorry. The critical value, that's where it comes from the table. And let's look at the table. And let's see what we have here. Aha. So under the table, the headings are normally N, alpha at 5%, and alpha at 1%. If I'm not mistaken, I asked us to test the hypothesis at the 5% level. So now I go to n equals 5. And across n equals 5 is 0.878 and 0.959. Remember, zero's in the middle. So let's suppose 0.878 is there. So that's our critical value, our cutoff value. And our test statistic value happened to be right here, which is 0.994. Okay, and the rule that I gave you earlier, so that's R. So R 994, which equals 0.994. That is greater than the cutoff value, the critical value. So we reject their null hypothesis, and we conclude that this data does show a linear correlation. So we do conclude that, so we reject HO, and we conclude that there is evidence that shows a linear correlation. Okay, let's look at another problem. When it comes to making up the headings for that table, don't go and memorize, oh, I need this heading and I must put that heading, and if I don't remember it, I'm not going to get it right. No, no. You Take your time. When you need it, you put it. Okay. Does there appear to be a linear correlation between mothers' heights and the heights of their daughters at the 5% significant level? So, if your mother's tall, and you're her daughter, are you going to be tall, or there's no correlation? So, mother's heights, daughter's heights, like X and Y. The mother's heights are 63, or mother's heights are 63, 67 inches, 64 inches, etc. 60. Actually, why don't we try to make this table a little bit smaller? The mother's heights are 63 and 67 and 64 and 60 and 65 and 67 and 59 and 60. And the corresponding daughter heights are 58.6, 64.7, 65.3, 61, 65, 67.4, 67.4, 60.9, and 63.1. I hope it's clear why one number is under another number. We have 1, 2, 3, 4, 5, 6, 7, 8. We talked to 8 mothers and their corresponding daughters. Mom 1 is 63 inches. Her daughter is 57.6 inches tall. Mom number 2 is 67 inches. Her daughter is 64.3, etc. We have 3, 4, 5, 6, 7, 8 pairs. Think of mom's heights as X's and daughter's heights as Y's. We'll think of the mom's heights as X's and the daughter's heights as Y's. There's absolutely no reason why you couldn't switch that. If you actually write down the formula for R and you switch X's and Y's, you'll notice, hey, it's exactly the same. Okay, so the formula once again is n times the summation of x times y minus the summation of x times the summation of y divided by n times the summation of x squared minus the summation of x all squared, the square root of that, times n times the summation of y squared minus the summation of y all squared. So we need to find out some things. Right? Need to know what n is. But n is the number of pair of datas, which is 8. So we know those 3. They're 8. Now, so let me write down the x's and the y's. 63, 67, 64, 60, 65, 67, 59, and 60. And the y's, 58.6, 64.7, 65.3, 61, 65, 67, 60.9, and 63.3. Now, I need to add up. That symbol just means add up. I need to add up x, y's. X times y's. Well, before I can add up x times y's, okay, this last number is wrong. It's 63.1. Before I can add up x, y's, I have to have the x, y's. So I multiply those two numbers, x and y's, and I already worked this out, get 3691.8. I multiply those x and y's, and I get 4334.9, then 4179.2, 4179, then 3660, and the last one is going to be 37. The next one is going to be 4225. The next one, 67 times 67.4, that's a typo. That's going to be 4515.8. The next one is 3593.1. 3593.1. The last one is 3786. So I add these up. The summation of xy, if I did my arithmetic right, is 31985.8. Okay, so I have that. N times the summation of xy, 985.8. Minus, says minus, now it says to add up x's. So you add up the x's. The summation of x's. You go to that column, you add it up, and you get 505. 505. Okay, 505. Times what you get when you add up y. Amazingly, when you add up y, you just get 506. Okay, so that's what I multiply by. 506. Then you divide this by those two square roots. The first thing under the square root is n, which is 8, times the summation of x squares. My goodness, I don't have a column named x squares. So you see, you don't have to remember the columns. They're given to you. You have to know the summation of x squares. So now I take all these x's and I square it. 63 times 63 is 3969. 67 times 67 is 4489. Then 4096. And then 3600. And 65 times 65 is 4225. 67 times 67 we already did. Don't bother doing it again. The next one, 59 squared is 3481. And 60 squared is 3600. And if I actually add up those numbers, and I don't make a silly mistake, we get 31,949. Okay, so that's what goes next to the n. 31449. Minus, does say minus, the summation of x, and then we square it. Well, the summation of x is 505. So you have to do 505 squared. And that's what goes underneath the first square root sign. The second square root sign, very similar, except instead of x's we have y's. The first thing is n, which of course is 8, times the summation of y squares. Well, I don't have the y squares. I have to make a new column, y squared. I take each of these y values and I square them. And if you did that and you add them up, you should get 32,063.32. And that's what goes here. 32,063.32. I ran out of space, but minus the summation of y squared. The summation of y is 506. and that has to be squared. And if you crank this all through, and you don't make any silly errors, which is really easy to do, I understand that. Make sure that what I wrote down is even what I have. Okay, if you don't make any silly mistakes, you should get that this is 0.69. So that's the calculated value for R. So do not, in my opinion, you should not remember the headings for this table. This is too complicated. And I can do these problems if I have the formula. Now, either you're going to have to know the formula or it's going to be given to you. But either way, you're going to have that formula written down on the paper, like I have right here. Either your teacher is going to give it to you or you're going to have to remember it. But either way, you have to write it down. Okay, if you can't write it down because you don't remember it and your teacher didn't give it to you, well, knowing the headings won't help anyways. Okay. So now what you have to do is find the critical value. The critical value, well, you have n, and you have alpha equal 0.05, and alpha is equal to 0.01. And we did say 5% at the beginning. So you look at 8, and you read off this number right here. Let me actually go to my chart, and when I look that up, I see 0.707. Actually, it's plus minus 0.707. So basically, you have negative 0.707 and positive 707. Okay. Now, it turns out that our value is the value that we calculated, our computational value, our computed value is 0.69. Excuse me. And that's inside here. Now, if you remember what you were told, let's get some space again, and we'll write this up nice and cleanly, and that will be done with this section. Now, let's see what we have. The absolute value of our R is 0.69. And this happens to be less than the critical value. In fact, it's less than or equal to the critical value, which is 0.707. Take the absolute value of the critical. Okay. Now, actually, you know what? Let's not even say it's plus or minus. How about saying the critical value is just always what's on the table? Okay. So we should label the absolute value on our table down here. So we are less than the critical value. Our computational value, 0.69, is less than or equal to the cutoff value. So their story says that we fail to reject the HO. And here, you accept HO, but you can't accept it, so you fail to reject it. And then you say that there is not enough evidence, there is not enough or sufficient. Sufficient is the same as enough. There is not sufficient evidence to conclude that there is a linear correlation. We cannot conclude that there is a linear correlation. So again, you need to understand, let me say this very, very clearly. Sometimes, since R can be between plus and minus 1, sometimes R will be negative. For argument's sake, let's just say R was negative 0.69. What you put on the table should be the absolute value of R. What you put on this diagram, I mean to say, should be the absolute value, which is 0.69, which goes right here. Or if you really, really don't like that, you can put over here negative 0.707. I got it from here. So, and negative 0.69, negative 0.69 is in between. If you're in between, if you're in between, you fail to reject HO. It's always been that way. So you have two ways of doing it. You can always take the absolute value of R and only have like a one tail. That is only put this line here. And since 0.69 is less than 0.707, our critical value, we fail to reject HO. The other alternative is the cutoff is, the critical value, the cutoff is negative 0.707 and positive 0.707. If your critical value, whether it's positive or negative, ours was actually positive. If it ends up in here, that is in between negative 0.707 and positive 0.707, you fail to reject HO. I think the last way I did it is cleaner, it's clearer, but I think most textbooks do it the first way. Just always, when you make this up, always put the absolute value. Because any negative number, like negative 0.993, is going to be less than 0.707, but there's a problem there. It's also less than negative 0.707. Okay. So it has to be in between the plus and the minus that you get from your table. All right, I hope I made that clear or clearer. And that completes this section.